Hello, I'm Nuno and I'm here to present the topic of my dissertation in engineering physics, which has to do with the development of GPU-accelerated trigger algorithms for the Atlas experiment at the LHC. Let's try to break this into parts. The LHC is obviously the Large Hadron Collider, which, depending on who you ask, may be known as one of the greatest common projects of the human race, as a really useful tool for particle physics, or as that big round thing where the nasty scientists are making enough antimatter to blow up the world. In all seriousness now, it has allowed us to detect the elusive Higgs boson, as well as probing increasingly higher energies for the possibility of undiscovered physics phenomena, by achieving collisions with center of mass energies up to 14 tera-electron volts. The Atlas experiment, whose acronym somehow comes from a toroidal LHC apparatus, is one of the two general-purpose detectors associated with the LHC, which means that it is equipped to detect and distinguish as many different kinds of particles as possible, some of them potentially still unknown. Because of that, it has to measure as many of their properties as possible, their momenta, their charge, their spin, you name it, which implies that the electronic systems that comprise it become quite complex and generate a hefty amount of data. The thing is, when a collision happens, the probability of a particle being created is not the same for all particles. Naturally, what we're really interested in are the rarest, because, well, they're rare, so they've either been less studied or not studied at all, which once again leads us to the realm of undiscovered physics. So what do we do to increase the number of these rare particles being detected? Simple, we do lots of collisions. In fact, the LHC is currently undergoing the high luminosity upgrade to more than triple the number of collisions that happen whenever the beams meet. And here's where the trigger algorithm part becomes relevant. Since the rate of collisions is so high, we simply cannot hope to store all the data from all the collisions, at the very least, because the electronic storage is not fast enough for it. Fortunately, most of these particles will correspond to well-known and well-studied processes, which can and should be filtered out. Thus, we must employ triggering algorithms that only register the kind of events that might be useful to our research. However, even these algorithms are strongly constrained by time, and if they were already struggling with a past number of collisions, after the high luminosity upgrade it will be even worse. As it's commonly known, there is little hope of creating electronic circuits that will enable us to process things faster, since current processors are already built as close to the maximum speed as possible. Our only option lies in processing more things at the same time, a trend which is taken to the extreme in graphical processing units, or GPUs. They excel in performing a large amount of relatively simple operations at the same time, like in linear algebra, since that is exactly the kind of stuff that is needed to display 3D computer graphics. While the CPUs, the central processing units that comprise most of the programmable devices we use, perform few, though possibly very complicated operations at the same time. Not all algorithms are easily translated from the CPU to the GPU, but those that can be usually benefit from a huge speedup, hence the relevance of GPU acceleration. So, to sum all of this up, what I will be doing for my thesis is looking into the ways we can speed up the triggering algorithms of the Atlas detector by performing at least some of the computations on the GPU, which will allow us to get a better selection of experimental data to further the study of rare events and with them, possibly undiscovered physics.